Good morning, everyone. Good afternoon, everyone. It's a short day. We're going to look at chapter 11 today. Just to remind you, tomorrow is a holiday, so there is no class. I will see you all on Friday. This chapter 11, we will be doing it today and on Friday, and that's all we need to do for the homework. So that's going to work out well. If any of you, because of the tornado warning, missed some of yesterday or didn't get in, everyone was given attendance, but I suggest you go and look at the video. It was quite a short thing. It was about 22 minutes because of all the interruptions we got. But you know, in case there's something in there that you've missed and you want to find out. So this last chapter is just taking it to the final level. We know how to find confidence intervals and estimate the value of a single mean. Now we're going to do the difference in two means. A lot of what we've done, the theory behind it, is very similar to the same theory when we looked at the difference between two proportions, right? So an awful lot of overlap, but nonetheless, let's just do, you know, basic what's going on. So imagine that you have two different groups. I'll call them group 1 and group 2. In fact, let's call them males and females because it's probably easier to distinguish. And we are interested in finding out, is there a difference between the males and the females? And we're going to measure something and find its mean, because it's the mean or the difference between the two means. So I get a sample of 100 males, adult males, and I find out that their average weight is 200 pounds and that the standard deviation is 15. And I get to call them 1, 1, and 1. And the females, they were 170. Their standard deviation was 25. And that I had a group of, say, 200 of those. So let's look at some of the technical terms that you're going to, you know, see or mention. This is a sample from a population, and it's a population, and the population here are males in, say, United States. And we use the term mu to be the mean. So mu1 would be the mean of this population. And can you imagine the same thing's true for the other group? And that's the mean of that group. Now, superficially, would you agree that there's evidence that males are heavier than females, which is probably true? I would say that's accepted in the science world, that an adult male is very often greater than a female. That's not true in the animal kingdom. There are a lot of animals where the female is actually heavier and larger than the male, right? But in the human race, it's males and females. And so we're interested in essentially estimating the difference between the two, right? Now we don't know these numbers. That's why we did the sample. So what we try and do is we try and create a confidence interval. And we do a confidence interval and we use that guy. Would you agree that the difference between the means should be close to the difference between these two, if our samples are pretty good? So what we need then is a formula for creating a confidence interval for the difference between two of them. And we've talked a little bit about this in the past. We need a guy called the standard error. As basically just another name for the standard deviation of the sampling distribution of these two. And it's made up of those two guys. So the standard error is this number squared divided by the sample size squared plus this number squared divided by that. Now, if I just isolated one of them, do you see how it says S1 squared over N1 squared? And I just said S1 squared, didn't I? Yeah. Over N1 squared. Are we cool with that? Right. So if you covered it up, you'd get your standard fella, which would be S over N. Now, where am I going with this fella? Okay, in this case here, this number is 15 squared over 100, and this number here is 25 squared over the other number. What is the other number? 200. I'm trying to find a question here because there's some bugging me. Because I did a version of this earlier and I want to see where my question is. Come on, I know you're here. Right, and so it is 225 over 100 plus 625 over 200.
Professor?
Oh, there's it is. I know there was some bugging me. For some reason, I put a square on those.
That's what I was going to ask. Thank you.
Yeah, that's the right numbers. Yeah, there was something there was bugging me and I couldn't see it, but we got it. Now, if you go to your calculator, you're going to have a really ugly looking thing, but the calculator can do it pretty quickly for you. 225 divided by 100 plus 625 divided by 200. And this guy is about let's say 2.3. X1 bar take away X2 bar is the difference between these two. So that's 200 take away 170, and there's 30. So that guy and that guy can create our confidence interval. Now, if I use the empirical rule, so let's do a 95% confidence interval using the empirical rule. The formula is going to be X1 take away X2 plus or minus a certain number of standard errors. For a 95% confidence interval, how many standard errors do you use? 95%, how many standard errors?
Two.
If it was a 90% not a 90, 99.7% confidence interval, wouldn't we use 3? So you put in a 2 here. Now, this guy here is going to be called the statistic in some of the questions. So you're going to get a question with a story like this, and it's going to say to you, what is the statistic? And you're going to put in the number 2.3. And it's going to ask you, what is the multiplier? And in this case, the multiplier is going to be 2. And I think the only one that is easy to know what they're on about is, aren't they going to also say to you, what is the standard error? So if they ask you for the standard error, it's going to be 2.3. If they ask you what the multiplier is, it's 2. And if they ask you what the statistic is 2.3. Are you comfortable now with the names that they give to these things in case there's a question where it just says, you know, tell me this number, tell me that number, and tell me that number? Are you comfortable with that? Right, now, we keep this thing going. It's going to be 2.3 plus or minus, no, it's not 2.3. That guy's 30. There we go. Is that why you were looking puzzled? It's 30. The statistic is this guy, and that guy is 30. So it's 30 plus or minus 2.3s. It's 30 plus or minus 4.6. That's going to be 25.4 up to 34.6. So the difference between males and females, right? The average male and female, the difference between them is somewhere in that range. Now, all these numbers are positive, aren't they? Great, they're all positive. Since they're all positives, isn't that evidence that males are heavier than females? Agreed? If the interval is all positive, the first thing is bigger than the second. Males are the first thing, bigger than. In a different question, a different animal perhaps, negative 10.7 to negative 3.6, wouldn't that mean that in this animal, the males are typically lighter than the females? Isn't that very similar to what happens when you talk about proportions? Right, the difference between two proportions. Now, there is a third possibility. Might as well change colour. Say again? What? Is that a question? No, okay. You could get negative 7.3 and positive 3.1. And in that case, don't you say that there's no evidence that they're different? Are we comfortable with the conclusion that you can get from a confidence interval, right? If they're all positive numbers, then the conclusion is whatever the first group is bigger than the second. If they're all negative numbers, whatever the first thing is, it's less than the second. And if it, what we call that, contains zero, then there's no real evidence that there's a difference. There's probably quite a few species of animals where the males and females kind of about the same weight, right? They don't vary much. And so far, so good. Now, empirical rule is really an approximation. We are going to look at doing a confidence interval, but we're now going to not use the empirical rule, we're going to use the t-distribution. So I'm going to choose another story then. So two populations. The first population is going to be people from Texas, and the second one is going to be people from Alaska. And we are going to find out, oh, what shall we find out? How many units of alcohol a Texan adult drinks and an Alaskan adult drinks? And we found out that in a normal week, and the average amount is 5 units of alcohol. I think a unit of alcohol is half a pint of beer, roughly. Right, so that's what the typical Texan does. And in my story, there were an 11 for the Alaskans. So the Alaskans, according to my story, drink twice as much as the Texans do. Right. Now, the standard deviation for Texans is 1, and the standard deviation for Alaskans is 4. Wouldn't you agree that there's a lot more variation in what Alaskans drink? Texans, not so much. And in this sample, it was only 100 Texans. No, 100's too big. There were only 25 Texans, and in this group, there was only 15 Alaskans. So would you agree that they are tiny sample sizes? And that's why we would use the t-distribution. Typically, even if they were big samples, we would still use a t-distribution. And the reason for that is if your data is coming from samples, just use the t-distribution and be safe. Now, we can construct most of what we need by hand, So today we're doing the by hand version, and then probably later on, maybe later on today, but definitely on Friday, we'll do the whole thing in salt. I'm now going to find the standard error. So it's going to be S1 squared over N1 plus S2 squared over N2. And so in this case, it's going to be 1 squared over 25 plus 4 squared over 15. And I'll do the standard error. And it's going to be the square root of 12 divided by 25 plus 16 divided by 15. And the answer I get.
1, Professor. That's 1 squared, not 12.
Whoa, thank you. And I don't know where my brain is. I just read it and didn't do anything. Entry. That will make a difference. So let's delete that guy. There. 1 squared, which is 1. And 16 is the right answer for the other one. So that's going to be, oh, that's quite a nice number. 1.1, 1.05, but we'll call it 1.1. Let's do a 95% confidence interval, but not with the empirical model, right? 95% confidence interval. I'm not even going to write it down, student t distribution, because almost all the questions will be. And it's going to be made up of x1 bar, take away x2 bar, plus or minus a guy that I'm going to call T star right now, times the standard error of x1 take away x2. Now x1 take away x2, x1 bar I should say, take away x2 bar is 5 take away 11. Plus or minus this funny guy called T star times 1.1. So it's going to be -6 plus or minus this funny guy called 1.1. T star is called the multiplier. If we were using the empirical rule, wouldn't T star be 2? Right. But we are going to use the student T distribution. That's, I guess, why that's called a T. T for student T distribution. And to get this multiplier, it's not as obvious as you think. You need to know a thing called the degrees of freedom. And in this story, the degrees of freedom are found by adding the two sample sizes together and taking away 1. In some books, it's add the 2 together and take away 2, but I'm going to go for the take away 1 version. And this is 25 add 15 take away 1, which is 39. So there's this magic number that you need. You'll also need to know what confidence interval you want. So in this case, we want a 95%. And we're going to take these two guys and we're going to use salt. We're going to use salt to find the multiplier. So I'm now going to take you over to here we are, our thing. Click on it. Click on this guy. There's, oh, are you looking at web assigned homework? Is that the screen you're seeing? Right. Now I'm going to hit the use salt one. Oh, darn it. No, too late now. Keep it on distribution calculations. Go here and do T distribution. You see it's asking for degrees of freedom, and that was the number 39. And I may have to shrink this down so you can see it. There. Go over here and do the betweens. And then go down here and tell it you want 95. Right, if you want 90%, put 90, but put 95. So let's show you what you do. T distribution goes here. Degrees of freedom go here. If you're looking for a multiplier, always use the between. And then go here and do, right, 95. And the multiplier is these guys. Now, do you see how they tell you plus and minus? Well, we always just write the plus version down. So I'm going to call this guy 2.02 to two decimal places. Are you happy about how we found that guy? Now, just for practice, I've got the right answer written down, but let me just pretend we do 2 or 3 more. Let's suppose a totally different story. The degrees of freedom were 120. And I wanted a 99% confidence interval multiplier. You see, I would change that to 99, and the number I would use then would be the multiplier 2.61. Let's suppose a totally different story, and I had the degrees of freedom of only 10. That would be a tiny sample, right? And I wanted to do a 90% confidence interval. I would do 90 there. And you see that my multiplier would now be 1.81. Are we comfortable about how you get that magic multiplier number, the T star? Just to remind you, the guy we just did a few seconds ago, the degrees of freedom were 39. And we were looking for a 95%er. And the number we're going to use is that guy. And I rounded him off to 2.02. Okay, I think we got that. So let's return to our question, because we're essentially doing 90% of this by hand, right? It's all done the good old fashioned way. Right, so now we know this fella. So back to our question. I'm going to switch places. And we have -6 plus or minus the multiplier times the standard error. And so it's -6 plus or minus, let's see what we get here, 2.02 times 1.1, and I get let's just call it 2.22. If we take this away, it's -8.22. And if we add it, it's -3.78. So our 95% confidence interval for the difference in alcohol consumption of Texans compared to Alaskans is somewhere in that region, right? Would you agree that all these differences are negative? What's that evidence of? If all the numbers are negative, what's that evidence of?
Texans consume less alcohol than Alaskans.
And then you could write some, I don't know, article in a newspaper or something, and you'd say, well, new research, Texans drink less than Alaskans, or whatever. Of course, can't you phrase that the other way? Alaskans drink more than Texans. It's the same information. But we tend to do it in terms of first guy compared to second guy. Do you feel comfortable about the process that we're doing by hand? Are you getting a feel for the flow? Right. This is the new guy in town, right? Coming up with this multiplier. Do another 1 against 2. What will we do this time? Let's do urban and rural. And what we did in these two groups, right? Urban are people who live out in the countryside, right? And wrong way around. Urban people who live in cities and towns, and rural people who live in the countryside, right? And we found out, what did we find out? We found out what the average cost of gasoline is. For people who lived in urban areas, I guess you would find like 20 gas stations, right? So N equals 20. And that the average price was $3.51. And then you found, rural areas, and you found, I'm sure they've got gas stations, right? Every place is, eventually you'll find a gas station. And we found 40 of those. And we found that the price was $3.81. And the standard deviation was 0.7, and the standard deviation here was 0.3 in N1 and N2. So you've got two different samples, right? 20 gas stations in urban areas, $3.51 was the average price, and the standard deviation, right? In other words, the variation in price was about 70 cents. In the rural area, it was a bit higher, right? $3.81. Variation there was only what, 3.30 cents, give or take. And there was a lot more. For some reason, you found 40 of those. And we are interested in, let's do a 99% confidence interval using a t-distribution, right? So we are going to find that guy. So let's get the statistic, which is the name we give to x1 take away x2, and that's 3.51 take away 3.81, and that ends up being negative 0.3. We're cool with statistic, right? And we need to know a standard error of this. And the standard error is that ugly S1 squared over N1 plus S2 squared over N2. And we go to your calculator and we do square root of S1, which is 0.07 squared, divided by N1, which is 20, plus the other one, 0.3 squared, divided by 40. And the answer I get is 0.16 roughly. And then the multiplier. So that's the standard error. But now we need to find the multiplier. Now, I need to know the degrees of freedom. Now, it's 20 plus 40, take away 1. So the degrees of freedom are 59. Are you comfortable with how you get degrees of freedom? And so the multiplier, and the confidence interval was what, 99%. So as long as we know those two things, we can go and look it up in SALT. So let's return back to SALT and see whether or not that comes out well. Okay, t-distribution is all set up. Degrees of freedom are 59. Oh, will you make sure that when you're doing multipliers that you're in distribution and not inferential? It'll look very similar, but you won't be able to get the magic T, right? The multiplier. So the distribution goes here. So I am looking at 59 and I'm looking at 99. And the number that comes out, would you agree it's 2.66 and some stuff? So the multiplier is 2.66. That's it. We got everything we need. Let's put it together and see if we can come up with a conclusion. So I know the difference, I know the standard error, and I know the multiplier. So our 99% confidence interval for the difference in prices in these two areas is going to be x1 take away x2 plus or minus the multiplier times the standard error. In our story, it's negative 0.3 plus or minus 2.66 times 0.16. Now that's negative 0.3 plus or minus, and I'll multiply those together and see what we get. So it's 2.66 times 0.16, and I'm making that to 2 decimal places because it is kind of money. And let's see what you get. If you take that away, you get negative 0.73, but if you add it, you get positive 0.13. So the difference between urban and rural gas prices differ by negative 0.73 or up to and including 0.13. Does that interval give you any evidence that they're different? No, it doesn't. What's the problem? Doesn't that interval contain 0? In other words, it's got positive and negatives. And when you have positive or negative numbers, there's no evidence to show there is a difference. So you might well be saying, it's kind of obvious people who stay out in the countryside pay more for gas than those in the city. You might even think it's the other way around, right? But the evidence that we've collected hasn't been able to show either of those two. Now, if I wanted to get evidence without cheating, wouldn't the only thing I could do would be increasing the number of people, right? The number of gas stations in this case that I used. So I'm going to pretend for this question that we actually did really massive samples, right? 200 gas stations in cities and 400 gas stations, right, in other places. And we're going to go through this calculation one last time. It'll probably be the last one for today. I'm pretty sure it is. Do you think that if these numbers are the same, and the only thing I did was I used much bigger samples and I got those numbers when I did it, do you think there might be evidence this time? So if you can't tell with a small sample, you think you might not be able to tell with a big sample, or this sample's just not big enough even right now. Let's find out. I don't know. Well, we can keep quite a lot of the numbers, and we have to change 2 of them, but we can at least keep the first one. The statistic, which is x1 bar take away x2 bar, is still negative 0.3 because it's the same 2 numbers. The standard error is going to change. Do you think this standard error is going to be bigger or smaller than that number when we increase the samples by a factor of 10? Bigger or smaller? What do you think? No committers? Christy, what do you think? Do you think this is going to be bigger or smaller? You're not sure.
Probably smaller.
Right. Seems reasonable. Would you agree if you divide by bigger numbers, you tend to make answers smaller?
Yeah.
That seems reasonable. I'm on your side. Square root of 0.7 squared divided by 200 plus 0.3 squared divided by 400. And I get 0.05. That is a big difference, isn't it? From 0.16, it's about what, 1/3 the size. Now, the multiplier, the guy that's called T star, he's actually going to be a different number now. The degrees of freedom are now 200 plus 400 take away 1, and that is quite a different number. It's 599. Great. And the confidence interval is still 99%. So I'm just going to do that here, so I don't need to jump back and forward. I'm going to put in 599 for the degrees of freedom, and I'm going to keep that as 0.99, and the number that I have is 2.58. Do you see it's a little bit different? Not a huge amount, but would you agree it's different? So our multiplier changed when the sample size changed, our standard error changed, and that stayed put, at least in this story. So I'm going to put the whole package together and see what we get. A 99% confidence interval. So it's x1 bar, take away x2 bar, plus or minus the multiplier, times the standard error. And this difference is negative 0.3 plus or minus 2.58 times 0.05. So it's negative 0.3 plus or minus 2.58 times 0.05, and I get plus or minus 0.129, so I'll call it 13. If you take it away, you get negative 0.43, and if you add it, you get negative 0.17. Have you noticed that the interval now is nothing but negative numbers? And when your interval contains nothing but negative numbers, doesn't that mean the first thing is smaller than the second? So in our case, what that is telling us that we have evidence that the price of gas in urban areas is less than what you would get in a rural area. So people in towns pay less money for gas than people in rural areas do. Do you see the difference a sample size could have on your conclusion? And so the moral of this story is always try and do your samples as big as you can afford, right? Because you're going to have time constraints and financial constraints. But if you were in the business of collecting data, try and get the biggest samples you can, because those are the ones that are likely to find differences, if differences exist.